Hello, welcome. My name is Ozan Gökhan, and I came from İzmir Biomedicine and Genome Center. Before starting, I want to shortly introduce myself. My bachelor's degree is from computer engineering, and then I've got my master's degree from Department of Electrical and Electronics Engineering. I'm currently a PhD candidate at the Department of Biomedical Technologies in Turkey. So today in here, I'm going to talking to you about the automatic classification of melanocytic skin tumors based on hyperparameters optimized by cross-validation using support vector machines. Skin cancers has an aggressive type of cancers, so we have to prevent this type of cancers. That's why, in terms of contributing to our clinical applications, we just investigate the capability of artificial intelligence-based developments using machine learning. So I have an agenda for you. First of all, I'm going to give you our overview of this study, and then some statistical informations will be given on skin cancer. Also, I have a Lesion Dataset that we use during training our algorithm. And then I'm going to talk to you about our used machine learning algorithms, why we choose machine learning. And then I will talk to you about our methods and results, future plans, and then I'm going to conclude my talk in here. So here's the overview. Imagine we have an unknown image or test image. I'm just asking to my computer. So the computer is going to respond the result of test image. So this is the whole study, can summarize it. Some statistical informations are an important criteria for development of artificial intelligence-based applications. So here is a couple of skin cancer informations. So melanoma and non-melanoma skin cancer are the most commonly occurring cancers in men and women, according to American Institute for Cancer Research, and also according to World Health Organization, between 2 and 3 million non-melanoma skin cancers and melanoma skin cancers occur globally each year. So that is that's really important to contribute to clinical applications using artificial intelligence-based approaches. So we have a Lesion Dataset that is open access, publicly available, and histopathologically verified. That contains, of course, that includes non-dermoscopic images. They include 70 superficial spreading melanoma and 100 nevocellular nevus. All images originate only from patients in Netherlands, according to this paper. So in terms of segment a lesion, it's important to analyze the peripheral region of a skin, because it's not important only considering the inside of the lesion, but also we have to consider the peripheral region of a skin. For example, in this slide, we can consider the small part of the patterns that we have to consider during classification procedure. And also, this study investigates the segmentation results for ground truth and the algorithm result. Mostly, the algorithm results are not matched with the ground truths. So, and also, I can say that we have to consider the peripheral region during extracting some meaningful features for classification purpose. So why did we select machine learning? Well, methodologically, there are a couple of properties for that. For example, depending on MetNode dataset, we have small dataset. And also we use hand-engineered approach for feature extraction. But on the other hand, deep learning is a feature extractor, but it has a more complex network structure. In this study, we didn't prefer to use deep learning. we just use this small data set, but we try to increase our future data set for the training our algorithm. There's another study that is convolutional neural network-based image classification. So they used whole slide images. Depending on some filtering approaches, they created different combination of lesion patterns, and then they created features. So they use whole slide images. So when we look at the MedNote data set, we can use whole slide images without any segmentation purposes. And we can use some textual patterns, some oriented patterns to create meaningful features in terms of training process. I have methods and results for you. For example, we use just only RGB image. After a gray image, we analyze in spectral domain. In spectral domain, as you can see, a frequency level features can be analyzed, and some periodic patterns, and also globes, dots that can be occurred in classical skin lesions can be analyzed in spectral domain. And then we calculate the co-occurrence matrices in terms of finding the probability of occur of gray level pairs. I'm going to explain how to calculate this matrix. And then we extracted textual features. And also, we eliminated non-zero values. We just focused on the region of interest for the calculation of textual features in terms of simplifying pre-processing step. We didn't use any lesion segmentation. We just only considered the whole slide images in terms of evaluating the classical ABCD rules, 3-point checklist, 7-point checklist that include asymmetry, color, regressions, atypical network structures, etc. So let me get back in the MedNote data set. I have a couple of melanoma type images in here. As you can see, the PSD images of melanoma can be characterizable in terms of frequency level stage. So in original images, if a periodic patterns or dots or strays can be occurred, I can easily analyze in power spectral density domain. And also in nevus, we have also some small derivative of lesions around the skin lesion. So we have to analyze that kind of criteria, and we have to create features considering the derivative of small particles of the main skin lesions. Here's the co-occurrence matrix step. How can we calculate the co-occurrence matrix? So imagine we have a 4x4 gray level image. We can calculate the reference and neighbor pixel pair, and then we fill the empty matrix with counting the repeated pairs depending on 4 different angles and 4 different distance values for this study. And then in terms of fast classification purposes, we normalize our co-occurrence matrix. As you can see, for example, in the top left box, we count the 2 number, which means 2 repeated 0, values occurred in this case. So 2 divided by the whole sum of red values is our normalized value. So after this step, we can calculate the textual features from normalized co-occurrence matrices. So in terms of summarizing the whole algorithmic stages, we considered the 170 MedNote data set, and we calculate the PSD images of each single MedNote image. And then we create co-occurrence matrices, and then calculate the feature matrix for each single gray level co-occurrence matrix. and then we collect together to prepare for the classifiers for binary classification purpose. So let me introduce a little bit about the support vector machines. We use two different classifiers. Here is the two different graphs that I want to show you. The solid line refers to a hyperplane or decision boundary. SVM aims to find a maximum hyperplane margin. Margin means distance between support vectors, which is closest to the margin. So here is the important hyperparameters that we tune during the training, fast training, and getting better accuracy results. For example, C or regularization or penalty parameter is controlling a trade-off between misclassification term and decision boundary. Larger C means smaller margin and vice versa. And also the gamma factor sets the width of the bell-shaped curve, which means decision boundary in this case. Larger gamma means narrower bell and vice versa. So depending on the mathematical background of these hyperparameters, we can easily understand how to control these hyperparameters. And also we have a pseudocode in here. We have a nested loop in here for different regularization factor, for different gamma factor. And we, at the end of this algorithmic approach, we selected the best hyperparameters that provide best cross-validation accuracy results. Our second classifier is a random forest classifier. This approach creates small decision trees on randomly selected subsamples from our main data set, which is our future data set, not image data set. In this case, in future data set. Each decision tree makes prediction according to ensemble learning approach. And for majority voting, final prediction can be selected. And this procedure is also called bagging or bootstrap aggregation. The main purpose of using this approach is to reduce variance, and of course it prevents the overfitting issue. For SVM, we use tenfold stratified cross-validation, and each step we split our data set into train and test, 80% for training, 20% for testing, and we achieved the accuracy values for each step, and we averaged them. And we achieved the performance metric. In this case, is called receiver operating characteristics. X-axis refers to false positive rate, true positive rate, Y-axis refers to false positive rate. So each fold, we achieve the area under curve values. Those values are stable after tuning and select better optimum kernel selection. We also have receiver operating characteristics for random forest classifier. In terms of summarizing the classifier's performance, first of all, we made holdout validation before tuning our hyperparameters, and then we cross-validated using tuning, and we achieved a better results when comparing with holdout method. And also we want to compare the Giolis et al. Who published data set. We have two different future plans. One of them is to extract image collection from different hospitals for testing in terms of providing generalization of our training model. And we have a second future plan in terms of creating fully autonomous systems. In this case, we will want to develop an end-user application called mobile-friendly web application, AI-based, of course. Imagine if you use smartphone camera, we can capture the image, and then web server can resolve fastly whether the image is melanoma or nevus in this case. This server has several capabilities. For example, I can run multiple CAD algorithms in this server side and automatically send these results emailed to a doctor or a patient. Server can be integrated with hospital integration automation system and access hospital data archive system with database management system and so on and so on. So lastly, I want to conclude my talking. So we aim to use dataset into two different classification. It's called binary classification. We simplified pre-processing step in terms of fast calculating, fast acquiring training result, test result, I mean. And then we tune our hyperparameters, and we did cross-validation for providing generalization of a model. Of course, all of these steps was to reduce unnecessary excisions and reduce biopsy procedures or to prevent misdiagnosis in clinical applications. Thank you for listening. I'm ready to get the questions if you have.